Hello nature lovers, Bob Ellis here, and I want to welcome you to the next episode of Notes from the Field. Today we're in the Ocotillo National Forest. We're right on the edge of West Clear Creek, and then we're in the West Clear Creek Wilderness. Behind me you can see the beautiful formations of the Sycamore group. It's nice red contrasting with a blue sky, and that formation that sits on top of the Hinky group, which is a basalt formation. Now today, we're not out here to talk about rocks. What we're out here to talk about is an environmental gradient. Now you might not know what an environmental gradient is, but it is a change in conditions over distance. And so we're going to look in the change in conditions over a distance with respect to moisture. We're going to investigate an environmental gradient focused on moisture, moving from creekside, which is mesic, to the uplands, which is xeric. And we're going to look at the plant adaptations that have been selected for out in this environment. Before I get started though, I really want to remind you, if you like this content and you want to keep it coming, the only way we can make this happen is by you hitting that subscribe button. That tells us that we're doing the right thing with this content. So go ahead right now before we get started and hit that subscribe button. Oh my goodness, how fortunate we are to be out here on this beautiful autumnal day, thinking about ecology and thinking about natural history. We're also thinking about this transect that runs from the streamside of West Clear Creek into the uplands, and looking at plants and the adaptations that have been selected for in those settings. The reason I really like to kind of frame natural history around ecological principles or concepts is the fact that it gives you some insight into natural history by having some big concepts like an environmental gradient to plug into. And so this is a perfect place to be thinking about this idea, because what's being selected for in the plants down here streamside is very different than what's being selected for in the uplands. So let me introduce you to a few of these plants down here and ask you to think about characteristics of these plants that serve the plant, that allow it to be successful. The first plant that I want to talk about is a plant that I've already introduced you to in an earlier episode, and that's this velvet ash or Arizona ash. This plant is as with all these other plants, are going to be found down here with their roots always in water. And so they're obligates. They are obligated to be in this situation. With this Arizona ash, notice that I'm going to take a leaf from the stem, and with this leaf, it looks like I've pulled off a number of leaves, but really these smaller leaves are leaflets, and this whole thing is a leaf. And you might be thinking, my goodness, Bob, what advantage is there to have? Why would that be selected for? Why would there be a lot of little leaves that make up one leaf? Well, the thing to know is that there is an optimal temperature at which photosynthesis takes place. And that temperature, believe it or not, is relatively low in comparison to the typical air temperatures out here in the summer. Down here, air temperature could reach 100 degrees. The optimal temperature for photosynthesis can run between 70 and 80 degrees, depending on the species. So that's a lot cooler. The plant has to have some mechanism to cool that leaf off, or it's not going to very effectively or efficiently photosynthesize. So in this case, what has been selected for, instead of one just big fat leaf, leaflets are selected for, because this allows the plant to cool. The boundary layer, the insulating layer of air that is around the plant, is broken up, disrupted by the fact that there are multiple smaller leaflets that allow the air temperature or the surface temperature of this leaf, or the internal temperature of the leaf, to be much cooler than the air temperature, and that confers it an advantage. Now the next plant that we want to think about is this willow. This is a red willow. It is Salix flavigata is the scientific name. This plant, along with all willows and a lot of willow lookalikes, solves the problem of surface temperature or internal leaf temperature by growing a long, skinny leaf. There is an enormous advantage in transferring heat if an organism is long and skinny or a structure is long and skinny versus something that is round. So the next plant I want to introduce you to is this beauty right here. And folks who are familiar with the Mogollon Highlands and streams in Mogollon Highlands will know this one, although this is a young one. This is Arizona Sycamore. It's Plantanus wrightii is the scientific name. And it too has some of those characteristics that we spoke about previously that confer an advantage. The strategy down here for plants is to grow tall, because the limiting factor here isn't water. There's plenty of water. The limiting factor is space. And the way to dominate space is to get ups. That means get tall. Get up and over your neighbor, and you can take advantage of all that sunlight. And the whole story here is capturing carbon. The more carbon you can capture, the more you can convert that carbon into growth form and therefore get tall and be a winner. And so this plant does that with these enormous leaves. A moment ago I was talking about leaf shape and how a compound leaf confers an advantage because it breaks up the boundary layer of air, and how a willow leaf, long and narrow, also does that. You might be thinking, well, Bob, I'm looking at those big leaves and I'm not seeing those characteristics. Well, in general, that's true. Whenever sycamores are young like this one, they do tend to have much larger leaves. And of course, that would be selected for to get an early advantage in that leaf temperature trade-off in leaf size makes a difference for this plant early days. In its adult form, those leaves will be a bit smaller. The way this plant kind of deals with heat, the physiological stresses of heat, is to have lobes, multiple lobes. So that too kind of is like a compound leaf. Those lobes break up that boundary layer of air surrounding this plant, allowing it to cool itself off. And once again, that's a big thing whenever your air temperature is around 100 degrees. All right, now this plant is special, and it's special in a lot of ways. And lucky for me, I found a small one, because these trees grow to be enormous. And this one is the Arizona Alder, or the scientific name Alnus oblongifolia. Now this plant is particularly interesting because a characteristic of this plant has evolved over the millennia that confers an advantage to it that other plants down here don't have. Now, one of the characteristics of this zone, as you look around and might have noticed by looking at the footage, is that this streamside floods, and in some cases floods enormously. Thousands upon thousands of cubic feet per second will rush down and crush these trees, blow them out. And so these plants have evolved with characteristics that kind of have a way of dealing with that disturbance. And this plant in particular's way of dealing with that disturbance is being able to crown sprout, or once the top gets cut off of it, maybe through a flood, or branches ripped off of it, it will come back. And it's usually one of the first plants that shows up as a seedling whenever a zone has been blown out by a flood. And the reason that it's successful early days is because it has a partner. It has a symbiont. It has bacteria in its roots that they've kind of brokered a deal. And the way this deal works is the bacteria in the roots are able to take diatomic nitrogen, which 78% of the atmosphere is composed of, and break apart that nitrogen bond. And the nitrogen bond is terrifically strong. It's a triple bond. So I like to think of that nitrogen is kind of guilty of malicious self-love or narcissism. And it's a macronutrient. Nitrogen is a macronutrient for all plants. So in other words, it is absolutely required and quite frequently a limiting factor in most biotic communities. And so the way this Arizona alder has solved the problem of having access to nitrogen whenever a big flood blows through is to rely upon its symbionts in its roots. And these are actinorhizal species of bacteria. And they're these filamentous kind of bacteria that live in the nodules that they form on the roots of the plant. And this is a mutualism. The tree gets nitrogen in the form that it can use, maybe NH3 or NH4, and the bacteria get sugar and nutrients. And believe it or not, the bacteria require about 10% of the photosynthetic take of the plant. So I always like to think of that as the plant tithing to bacteria in order to have an advantage in these newly created environments. All right, well, we moved into the uplands, and almost immediately you see many differences in the vegetation and what's being selected for. Perhaps you can hear the stream sound in the background, and maybe see the stream vegetation, and all that deciduousness when we move into the uplands drops away, and we move into the realm of persistent leaves or evergreen leaves. And in the case of this plant, this pinyon pine, Pinus edulis variety Phalanx, you can think of these needles as leaves. And so they are modified leaves, and they're very tiny with, in comparison to the deciduous leaves that we found down by the water. So as we move up this transect, or we move up this environmental gradient into the uplands, the first thing that you're noticing is that deciduousness drops away. There are very few deciduous plants here in the uplands, and the idea of a persistent kind of evergreen leaf becomes much more obvious. Another plant you'll encounter in the uplands has many of the same characteristics of that pinyon pine, and that's this juniper tree here. This is Juniperus osteosperma. People call it Utah juniper. And if you look very closely at the leaves, you would see that they're kind of modified scales. They are absolutely tiny. The big advantage of having this reduced leaf size and small leaves is, once again, surface area cools off because of smallness. And then the other thing is, no longer are you losing moisture, because losing moisture in the uplands is a death sentence. The reason that it's a death sentence is simply because in order to capture carbon from the atmosphere, CO2, a plant has to keep its leaf openings open. And these leaf openings are called stoma. If the leaf openings are left open, that allows water to escape from the plant. So every adaptation up here in the plants that we're going to see have modified leaves or some modified photosynthetic pathway that allows them to persist in a landscape where their roots are not in water. And yet they're able to capture carbon. Okay, we're up here in the dry uplands, getting drier, and I'm about ready to quit. It's so dry, but I'm going to stick with it because the plant that I want to introduce you to here is not a single plant, but a family of plants, and a fascinating adaptation that has been selected for. So as it gets drier, plants have to figure out, if you want to use an anthropomorphic term, ways to deal with this dryness. This family of plants, grasses, Poaceae, oh my goodness, they have a whole host of characteristics to accommodate dry conditions. But the one that I want to focus on is the evolution of a photosynthetic pathway that is different than the pathway of the plants that we were seeing down Streamside. The Streamside plants use a photosynthetic process that is called C3. And basically, it's a very, very water wasteful process. However, here in the uplands, a whole different photosynthetic pathway with a whole different enzyme in place has evolved to accommodate the conditions up here. And a lot of grasses are C3, a lot of grasses are C4, and as a matter of fact, there's some grasses that can move between C3 and C4. But most of the grasses in the upland here are C4, and what has happened is that there's this whole different biochemical pathway has been selected for that allows for conservation of water or more efficient water use. And so grasses are king and queen of dryness. I have these sunglasses on because it is bright up here in the uplands. So, a plant that is dominant in the uplands across the Mogollon Highlands are prickly pears. And prickly pears are in the genus Opuntia. And once again, the power of evolution is just magnificent, because with this species, as well as many other succulents, that means that they have these fleshy stems or fleshy leaves, because in fact, the spines on this plant are modified leaves, and the flat pads are modified stems. So this plant is photosynthesizing with its modified stem, which is a big advantage because you don't have leaves. However, you do have the problem of capturing carbon. And capturing carbon becomes more difficult because there's less water, and you don't even have leaves, or the plant doesn't even have leaves to photosynthesize with. So what does evolution select for? A whole different photosynthetic pathway. And this pathway flips the whole thing around in a way that this plant is photosynthesizing at night. So, champion of dryness, Opuntia. You know, maybe I should say one of the champions of dryness, because in the background you can see an agave. And same kind of story, that they have these fleshy leaves where they are able to reduce the amount of moisture that they're losing through a whole different photosynthetic pathway than the pathway that we found down at Streamside. Wow, we encountered a plant that we didn't expect to see. We've encountered a plant of the hot desert, a plant that you'll find in both the Chihuahuan and Sonoran desert. So this is really speaking to a hot, dry climate. And that is this plant, Ocotillo, or Focieria splendens. And look at the adaptations of this beast. Oh my word. You're probably thinking, well, Bob, that thing's dead. Well, it sure looks dead, but one of its adaptations is the only time this plant is going to put on leaves is when it rains. So it seems to be dead, but really just dormant. And whenever rains come, it's going to flourish with leaves and with flowers that are, well, the species epithet, splendens, describes the flowers, which are splendid. They're beautiful, beautiful red. But let me tell you, Ocotillo might be the lord of dryness. Hey everyone, thanks for going on that little environmental gradient adventure. Hopefully you found out some things that might help you in the future whenever you walk into other settings where you see such an environmental gradient. It is always fascinating to frame your natural history observations around these big ideas, because I think it does give you clues about what you're seeing and the evolutionary past of these organisms. So thank you once again. And by the way, if you didn't hit that subscribe button at the very beginning of the video, now's your chance to do it. And if you really like what we're doing, why don't you go to our website, naturalhistoryinstitute.org, and there's a donate button there that you can push and help us keep these notes from the field coming to you. Thanks again.